Hi everyone, this is an introduction to our series unit. The very first question we're going to ask you is, what is the function that represents this graph shown here in Desmos? If you're looking at the different properties, you might think this might be the sine graph, given the periodic nature of it. If you notice, it does go through 0, 0. We've got this high point up here at pi over 2, 1. As we come down to the next 0, though, you'll notice that it intersects at 3.142, not actually at pi. And if we keep going down here, you'll notice that we're not quite at 3 pi over 2. And over here, this isn't at 2 pi. So you might be asking yourself, what's kind of going on with that? If this isn't sine of x, what actually is it? If I also zoom out a little bit, you notice that it doesn't quite resemble sine of x as we go further and further away from 0. This is actually a polynomial function. Polynomial functions are any of those functions that are x to a certain power, something like x squared, x to the third, x to the fourth. You'll notice that this does have an end behavior that as x approaches negative infinity, f of x approaches negative infinity, and as x approaches positive infinity, f of x also approaches positive infinity. It has different end behaviors like polynomials would. So how did we create a polynomial that looks like sine of the x when you zoom into it, but still behaves like a regular polynomial elsewhere? That's kind of what the series is all about, is that we have this idea, this snapshot of a function that is not polynomial, but we can actually use a polynomial equation to resemble it, to basically mimic it. And that's what we're creating here with series. So we're going to switch over to a different function that's a little bit easier to work with in terms of the equations, and it's e to the x. So if we take a look at this picture right here of e to the x, and we just take a look at some of the other polynomials that we had originally used with e to the x. The first one was a linear function, a tangent line. So we're going to use the point of tangency 0, 1 as our point of tangency that we're going to use for all of these different polynomials. The very first polynomial we created was linear, which was our tangent line that we referred to so often all throughout of calculus. And you can see that as you get closer and closer to 0, the tangent line is a pretty good approximation for what happens with e to the x. I mean, you have to zoom in pretty close to say that along here, it's pretty similar to each other. And if we look at some of these tables of values at 0, f of x has that value of 0, and our approximation also has a value of 0. That's where it's tangent. And then if we move over a little bit, the function actually is 0.778, but our approximation is only 0.75. So again, pretty close, but not quite accurate. And the further out we go, the less accurate our line becomes. So this was kind of a troublesome spot for linear functions, is that it is really good for approximating really close to your point of tangency, but not so much in other locations. The further away you go, the less accurate it becomes. So the question is, if this is just a polynomial, what if we didn't use a linear polynomial, but instead, what if we went up a degree and used a quadratic? Here's an example of a quadratic function that resembles e to the x. So the purple is our tangent line, the green is a quadratic. So again, if you zoom in, the green quadratic does resemble e to the x right around x equals 0, as does the linear function, but it actually kind of resembles it a little bit further away. So if you kind of follow this, your tangent line purple kind of starts to waver a little bit, but the green kind of hugs e to the x a little bit better the closer you go. And this is happening because we have a higher defined degree, that we're using a higher degree polynomial. So I'm going to turn off the linear one and look at what happens with the values. Again, your point of tangency is 0, 1, so they both share those values. But the further away you get, you're getting a little bit more accurate. We have 0.778 again for f of x, but our quadratic is 0.781, so a little bit closer. And then even all the way at -1, we are still pretty much, again, it's a little bit further off the further away you go, but it's a much better approximation than what happened with the linear. So again, stands to reason, what would happen if we took this up another degree and looked at the third degree, or a cubic function? Here is what the cubic function would look like overall compared to e to the x. So here's your black e to the x. The orange is the cubic function that kind of hugs it really, really well. And if you look at these table of values, your point of tangency is 0, 1, and look at how much more accurate e to the x and the cubic kind of resemble each other the further out you get. Now, obviously, if you kind of go out even further, it's not going to be as good because the polynomial is going to have an end behavior. It is going to approach either positive or negative infinity, whereas e to the x does flatten out and have a horizontal asymptote of 0 on the left-hand side. So there is going to be some trouble there that if you stop at a certain degree, it's not going to be accurate for everything, but it can be really, really close approximation most of the way. So right here, we have a table of values to kind of compare all three of the approximations with the actual value. So f of x is your function e to the x. Here are all the different values we're trying to use to approximate it. The linear function, as you can see, is not very accurate at all. Even for going to negative 0.25, it's not very close. But the more degrees that you add, the more accurate that's going to be in your approximation. So if we went really extreme, let's say we wanted to go all the way up to a degree of 15 and try to take a look at what happens there. So right now we're going to start by turning on a linear function. So this is what the tangent line is going to look like. This is your quadratic. Here's your cubic, or actually this quartic. We jumped all the way over there. Degree 5, 6, 7, 8. And it keeps on going if I go all the way up to degree 15. So again, if you zoom out, you'll notice that the right end behavior really does hug the e to the x function really well. And on the left-hand side, it doesn't flatten out with a horizontal asymptote of 0. It kind of goes all the way over to about maybe negative 5.5 or so before it really starts to kind of veer away from the actual function. But look at what happens with the table of values. Here's e to the x. This is our 15th degree. These are all matching, aside from 7, the extra one that I threw in there. But if you look at the closer values, they're all accurate from negative 1 to 1. They are 8 digits deep, and they are still identical. When you get further out there, like in 7, or in some of the other values, like we changed this to be negative 7, you'll notice that the e to the x is close to 0, but our polynomial function is not. Again, this is one of the sticking points when it comes to polynomials, is that you can be very, very accurate with a higher degree, but you still need to be reasonably close to your point of tangency. In this case, it was at x equals 0. That, in a nutshell, is kind of what is going on with the series. So a couple of things that we're going to be looking at as we go through are these common types of series. How do we know where they're going to be identical to a function versus not? This crazy notation over here with the sigma, how do we make that? What is that built off of? We're going to be talking about how to create all of those. And then we're going to also talk about, more specifically, how do we know where this cutoff point is? If these two are going to be identical, if we're going to have a function that's not a polynomial and a function that is a polynomial, how do we know where they're going to be identical versus not? And that's kind of what we're going to be talking about in this unit. I don't know how to make this larger. Okay, so that in a nutshell, guys, is the 3 kind of main outlines that we're going to try to accomplish for this unit. We'll be back with more details. There's some other videos that you can kind of also watch that give you a preview into some of the things that you'll be doing as well.